So this is the worked answer to the unit success question 3. This question is about the height of a pole vaulter above the ground, and it can be modelled using this equation where height is this, and x is the distance, horizontal distance travelled after his feet leave the ground. Although it's not vital, I think it is useful to understand what pole vaulting is. So I'm going to quickly look at a video of an example. So what we are saying is that his feet coming up, and then going over the bar and back down. We are going to model that as a quadratic, and we're going to model it as a negative quadratic, because it's clearly a U shape, and this is the quadratic we're going to be using. So we want to find horizontal distance for when the pole vaulter lands, and we are told, given the pole vaulter is at its greatest height halfway between leaving the ground and his landing, find the greatest height of the pole vaulter. So very similar to the usual questions, I'm going to draw a picture of what we have. So we have a pole vaulter doing something like this. We have our x-axis, we have our height, and we are told that h equals 1 over 60, 125x minus x squared. So in the first, minus 12x squared. Let's put that in there. Okay, so in the first part, we are trying to find where does he land. So how far is this distance? So we can see very clearly that we want h to equal 0. So what we're going to do is we're going to say that this thing equals 0. If we times by 60, it's not going to change to 0. So what we're actually saying is this thing here equals 0. So 125x minus 12x squared equals 0. So we get x and 125 minus 12x equals 0. So either x equals 0 or x equals 125 over 12. And clearly it's this second answer that we want, because we knew he was standing on the ground to start with. In part B, they want the greatest height. They want this point here. And you are told that the quadratic is symmetrical, and you're told it is greatest height at half the distance. So what we're going to need to do is half this value here. So that means we want to know the height when x equals 125 over 24. So all we're going to need to do is substitute this value into here. It may be worth typing this into your calculator and pressing equals so it's saved as answer. So we can then write something along the lines of h equals 1 over 60 brackets 125 answer minus 12 answer squared. And assuming this is what is actually in the calculator currently stored as the answer, you'll get an answer which is 5.42. So that's part A and B done. Part C. For a jump to be successful, the pole vaulter must clear a bar of 4.9 meters. So like we saw in the video, they will actually go a bit above the bar, and he clearly does because he went 5.42. So this answer does make sense in context of the question. But there is a whole time, a whole space where he is actually above 4.9. So 4.9 would be here. And you can see he's first above it here, and he's last above it here. So what they're asking you to do in part C is find solution 1, solution 2, and say that he needs to be that far away from the bar in order to get over it. So what we're going to do is say h equals 4.9. Therefore, the equation we're trying to solve is 4.9 1 over 60 125x minus 12x squared. And this is the equation we want to solve. If I times by 60, I'm going to get 294 equals 125x minus 12x squared. And I'm just going to rearrange this so it's in the standard form of a quadratic, so it's equal to 0. So 12x squared minus 125x plus 294 equals 0. We're going to type this into our calculator and use a quadratic solver, and we get x1 equals 3.58, x2 equals 6.82. If you don't have the correct calculator, get it, but you could have used the quadratic formula and you would have got those same answers. So that means that he needs to be jumping 3.58 metres away or less than 6.82 metres away. If he jumps this distance away from the pole, he will be above 4.9 by the time he gets to the pole. Part D is just a definition question, and Part D asks you what the effect of modelling the pole vaulter as a particle has. And I would have said originally that by modelling him as a particle we can assume there's zero air resistance, but you can't really use that answer because it's given in the second part. So what we're going to do instead is think about how a particle behaves differently to a human body. And if you think about the rotation of the human, that's going to be completely ignored because it's being modelled as a sphere instead. So the limbs and the body being able to be modelled as a sphere is the point here, so we can ignore rotation. Making air resistance negligible just means we get to ignore the air resistance. So the only thing acting is gravity, and we get this nice quadratic that we was hoping for. So I, we're looking for no rotation, and I, we're looking for ignore air resistance.